Hello everyone, we are Team 11. Myself, Rajkumar Mehta. Today, I will be representing on non-preemptive priority scheduling with a real-life case study based on emergency room trial scenario. This topic explores how CPU scheduling in operating systems can be compared to real-life healthcare situations. Just like doctors must decide which patient to be treated first in an emergency, just like CPU decide which process to be executed based on their priority. So let's understand what CPU scheduling means. Scheduling is how the CPU decides the order in which process will execute. It's like a traffic controller deciding who goes next. In non-preemptive priority scheduling, once a process starts, it cannot be interrupted until it finishes. Just like a doctor completing treatment for one patient before moving to the next. Our main objective in this session are to connect this concept with a real life hospital emergency case, explaining how the algorithm clearly calculate turnaround time and waiting times, and discuss the pros and cons of this scheduling method. This real life scenario, hospital ER track. Imagine a hospital emergency room with only one doctor available. Patients arrive with different levels of urgency, some stable and some are critical. These constraints here is that once the doctor starts treating a patient, they must finish before moving to the another. This ensures no errors, just like a non-preemptive pressure in the CPU. The challenge is deciding who should be treated first and who should be treated next, balancing fairness and medical urgency. The connection is clear. This real life situation mirrors CPU scheduling. The doctors act as the CPU and the patients are like process with different priorities. So you can see all this in this slide.
Now I will explain you about mapping real-world problems to the scheduling terms. See, we need to consider it like an emergency room. When our patients arrive, they have different needs and wait time. This is very similar to how operating system works with the processes. A patient is like a process or a job that needs to be done. A patient is like a process that arrives at the emergency room at their arrival time. The time it takes a doctor to treat a patient is the burst time, or the CPU. The patient triage level will depend upon the condition or the priority of the patient. The doctor is the CPU itself. The waiting area is the red queue where processes wait for their turn. This analogy helps us to understand efficiently that how operating systems manage these processes. In the next slide, I will be explaining about non-preventive algorithm. See, in non-preemptive algorithm, the patient treatment starts. It can be interrupted until it is finished. In this, first we need to check arrivals. We always start by checking who has arrived first. Second, advance time. Advance time means if no one has arrived, the CPU waits and does nothing until a new process arrives. Third, select highest priority. Select highest priority means from all the patients currently waiting, we select the one with the highest priority. Fourth, run to completion. Once a patient is selected, they are treated until they are done. No interruption. Fifth, tie breaking. If two patients have the same priority, we use first come, first served rule. It means that the patient will get first treated who has arrived first. This method prioritizes urgent tasks, which is great, but it has a key trade-off. It could delay a new urgent arrival if the CPU is busy with a lower priority task. Now, in the next slide, I will be explaining about the case study. See, in this case study, we have choose four patients whose names are Alice, Bob, Carlos, and Diana. Alice arrives at time 0, needs 4 units of treatment, and has priority of 2. It is urgent. But Bob's arrives at time 1, needs 3 units of treatment, and has a critical priority of 1. Carlos arrived at time 2 and needs 1 unit of treatment and has a non-urgent priority of 3.
We have
Yeah,
understood the basics. Let's walk through the non-preemptive priority scheduling algorithm step by step. So we will be here seeing the Gantt chart, so we can know how which process are takes place from the queue in the processor and in what order and what is the completion time. So initially, as it is a non-preemptive priority scheduling, it should be according to the priority. But as we know, the priority of 2 is higher than P1, but still at the time 0, P1 is present in the queue, not P2, and we don't want the processor to be idle. So from time 0 to 4, P1 will be executed, and by the time P1 ends the process, we know that all the other processor has arrived in the queue. So after that, based on priority, P2 will be executed. Then based on priority, P4 will be executed, and then P3 will be executed. We can see here in the Gantt chart. First P1 is executed till the time 4, then P2 till 7, P4 till 9, and P3 till 10. That's we can see in the detail matrix here. Here is the arrival time, burst time, start time, and finish time. Finish time is basically the completion time, and this is the turnaround time, which has a formula of completion time minus arrival time. And then we have waiting time, which is equal to turnaround time minus burst time. We calculate the average turnaround time, which is 6 seconds, average waiting time, which is 3.5 seconds, and total completion time, which is 10 seconds. Now we can come into discussion. What are the advantages? The advantages we have is low overhead, simple implementation, predictable execution, and no race condition. Disadvantage is poor responsiveness. Starvation is a possibility here. And as this is non-preemptive, no allowed process can be stopped in between. It will be completed and then only other process could be executed. And this is a quick summary. The core concept is non-preemptive priority scheduling, performance analysis. As we have seen that the average turnaround time is 6 seconds and average waiting time is 3.5 seconds. And we can see the real world application ER triage, which we have used to explain here based on the patients. Thank you.